collision between two asteroids produces a fragment that is momentarily at rest at a distance r1 from the Sun. Under the influence of the Sun's gravitational pull, the fragment falls towards the Sun. Derive an expression that represents the time it takes to reach the smaller distance r2. So we have an object, a distance r1 from the Sun. It is momentarily at rest, so it has no velocity. With no velocity, it will free fall to the Sun. We'd like to find an expression that tells us how long it will take to reach a new distance, r2. The object is accelerating, so velocity is not constant in this problem. Acceleration is not constant either. Acceleration gets greater as the object gets closer to the Sun. But let's assume that over small distances, velocity and acceleration are constant. Now it's easy to find the time it will take to follow the short distance dr. Time equals distance over velocity. But how fast is it going at a certain distance? The object started with nothing but potential energy. It loses potential energy as it gets closer to the Sun. This potential energy turns into kinetic energy, so our velocity at a distance r2 can be found using the conservation of energy. The change in kinetic energy is going to be equal to the change in potential energy, which is equal to the final potential energy minus the initial potential energy. So this gives us 1/2 mv squared equals negative g m1 m2 over radius 2 minus negative g m1 m2 over radius 1. Every term has a small m in it, so the small m's cancel out. We don't need to know the mass of the object doing the falling. And we can also factor out the negative gm and we could take this 1/2, multiply both sides by 2, and I could solve for v alone by simply taking the square root of each side. So now I can get the amount of time it takes for this object to fall through a differential slice. By plugging it back into my original time formula, and the d in this case is going to become dr, the distance of the differential slice. And all of the differential slices added together will give me the integral from r1 to r2. And now I have my expression.